Astronomers detected an object entering our solar system at extraordinary speed. It was not orbiting the sun, it was not gravitationally bound, and it was not behaving like anything we had ever seen before. Then, before we fully understood what it was, it disappeared. If this object was natural, it was unlike any object ever observed in human history. If it was not natural, then something from outside our solar system passed through our cosmic neighborhood without warning and without explanation. In the next several minutes, you will understand exactly what astronomers detected, why the data immediately disturbed them, why the object's behavior broke multiple physical expectations, and why, years later, scientists are still debating what it actually was. This is not a story about speculation. It is a story about observation, uncertainty, and the uncomfortable limits of our understanding. In October of 2017, astronomers operating the Pan-STARRS telescope in Hawaii were performing routine sky surveys. Pan-STARRS is not designed to search for mysteries. Its job is simple and practical. Detect moving objects, asteroids, comets, near-Earth threats, anything that might cross Earth's path. During one of these scans, a faint object appeared in the data. At first glance, it looked unremarkable, small, dim, just another point of light moving against the background stars. But within days, astronomers noticed something unusual. The object was moving too fast. When scientists calculate the trajectory of objects in the solar system, they expect certain behaviors. Objects bound to the sun follow predictable elliptical orbits. Their speeds increase as they approach the sun and decrease as they move away. The math is reliable. It has been tested for centuries. This object did not follow that math. Its speed suggested it was not captured by the sun's gravity at all. It was moving on a hyperbolic trajectory, meaning it came from outside the solar system and would leave it forever. For the first time in recorded history, humanity had detected an interstellar object passing through our solar system. The object was named ʻOumuamua, a Hawaiian term meaning a messenger from afar arriving first. The name was poetic, the data was not. As more observations came in, the situation became stranger. Astronomers expected ʻOumuamua to behave like a comet. Most interstellar objects are assumed to be comet-like, icy bodies formed in the outer regions of star systems, later ejected into interstellar space by gravitational interactions. Comets approaching the sun heat up. Ice sublimates into gas. Dust is released. This produces a visible coma and tail, and, critically, it produces a measurable force that can slightly alter the object's trajectory. But ʻOumuamua showed no visible tail, no gas cloud, no dust plume, no cometary signature of any kind. Yet despite this, precise measurements revealed that ʻOumuamua was accelerating as it left the solar system. This was the first major problem. Acceleration without visible propulsion violates expectations. In space, objects do not accelerate unless a force is acting on them. For comets, that force is outgassing. For spacecraft, it is engines or radiation pressure. For ʻOumuamua, there was no visible source of thrust. This contradiction alone would have been enough to classify the object as highly unusual, but it was only the beginning. As astronomers studied its brightness over time, they noticed extreme fluctuations. ʻOumuamua's brightness varied dramatically as it tumbled through space. This suggested a shape unlike any asteroid ever observed. Most asteroids are roughly spherical or irregularly compact. ʻOumuamua appeared to be extremely elongated, possibly 10 times longer than it was wide. Some estimates suggested a shape more like a cigar or a flattened pancake than a rock. Objects like that should be structurally fragile. They should break apart. They should not survive long journeys through interstellar space. Yet ʻOumuamua showed no signs of fragmentation. Its surface properties were equally confusing. Spectral analysis suggested a lack of common ices and dust. The surface appeared unusually reflective, possibly hardened by long exposure to cosmic radiation. Every new measurement added another layer of inconsistency. Wrong speed, wrong acceleration, wrong shape, wrong surface. At this point, scientists were no longer asking what Oumuamua was. They were asking why none of their models fit. To understand why this disturbed astronomers so deeply, it helps to understand how conservative science normally is. Astronomy is not a field that leaps to extraordinary conclusions. When data does not fit expectations, the first assumption is always error. Instrument noise, measurement bias, misinterpretation. Scientists double-check. Then they triple-check. In Oumuamua's case, multiple independent teams confirmed the same anomalies using different telescopes and methods. The data was real. That forced scientists to consider possibilities they had never seriously entertained before. The simplest explanation was that Oumuamua was a natural interstellar fragment, debris ejected from another star system billions of years ago. This idea made sense statistically. Star systems are chaotic. Planets collide. Gravitational interactions fling material into deep space. Over cosmic time, the galaxy should be filled with such debris. But this explanation required several unusual conditions simultaneously. First, it required Oumuamua to be made of material that could sublimate invisibly, hydrogen or nitrogen ice, for example, producing acceleration without visible gas. Second, it required this material to survive a journey lasting potentially hundreds of millions of years through radiation-filled interstellar space. Third, it required the object's extreme shape to remain intact despite repeated thermal stresses. Each requirement was possible. All of them together were uncomfortable. Science can accept one anomaly. It becomes uneasy when anomalies stack. Another proposal suggested that Oumuamua was composed of hydrogen ice, a substance that evaporates without producing visible signatures. This could explain the acceleration without a tail. But hydrogen ice presents its own problems. Hydrogen ice is extremely fragile. It sublimates easily. Surviving interstellar space for extended periods would be extraordinarily difficult. Other scientists proposed nitrogen ice, chipped from the surface of a Pluto-like exoplanet. This model could explain reflectivity and some acceleration behavior. But again, it required very specific formation conditions and did not fully account for the object's shape. No single natural model explained all observations cleanly. And this is where the conversation changed tone.
A small group of scientists asked a question that is rarely voiced openly, not because it is forbidden, but because it carries consequences. What if Oumuamua was not a natural object at all? This idea was not presented as certainty. It was presented as a hypothesis of last resort. One possibility raised in peer-reviewed literature was that Oumuamua behaved like a light sail, a thin, reflective object pushed by radiation pressure from starlight. Radiation pressure is real. Space agencies have tested solar sails successfully. Under the right conditions, light alone can impart momentum. If Oumuamua were thin enough and reflective enough, radiation pressure could explain its acceleration without visible propulsion. This hypothesis did not claim Oumuamua was a spacecraft. It did not claim intent. It suggested the possibility of artificial debris, a fragment of technology, perhaps long inactive, drifting through space. There was no evidence proving this explanation, but there was also no data that immediately ruled it out. That fact unsettled many scientists, not because of what it implied, but because of what it revealed. Our instruments were not sufficient to know the answer. And then came the most disturbing part of the entire story. We lost it. By the time astronomers realized how anomalous Oumuamua was, it was already too far away. Its faintness increased rapidly as it exited the inner solar system, No spacecraft could reach it in time. No telescope could resolve its structure. Humanity's first confirmed interstellar visitor passed through our solar system, revealed itself as deeply strange, and vanished before we could understand it. This was not negligence. It was limitation. Our detection systems are designed to monitor threats close to Earth, not objects approaching from interstellar space at extreme speeds. ʻOumuamua exposed a blind spot. In response, scientists began asking an unsettling question. If ʻOumuamua passed through unnoticed until it was already leaving, how many others have done the same? Interstellar objects do not announce themselves. They do not arrive on predictable schedules. They do not slow down. They pass through quickly, quietly, and on trajectories we may never anticipate. Some may be small and harmless, some may not. This realization has driven the development of new telescopes, including the Vera C. Rubin Observatory, designed to detect faint, fast-moving objects earlier and more reliably. Not because scientists expect aliens, but because the universe has demonstrated that we are not as aware as we thought. ʻOumuamua forces us to confront an uncomfortable truth. Our solar system is not isolated. It is not protected. It is not static. It is embedded in a galaxy filled with wandering objects, remnants of distant star systems, fragments of violent cosmic histories. Something came here. We saw it late. We understood it partially. And then, it was gone. That should not terrify us, but it should humble us, because next time, the object may be larger, or closer, or stranger. And whether it is natural or not, the universe has made one thing clear. We are not watching as closely as we think.